This is the 14th lecture of this course and the third lecture on carrier transport. In this lecture we will be completing the discussion on this topic. In the last class we saw that for small electric fields the drift current is proportional to the electric field and mobility is the constant of proportionality coming in this particular relation between current and electric field. Similarly, we saw that for small concentration gradients the diffusion current is proportional to the concentration gradient, and the constant of proportionality here which comes in is diffusion coefficient, of course with other terms also coming in. Now we also saw that the mobility and diffusion coefficient are related by the Einstein relation, and then we said that since the diffusion coefficient is related to mobility, if we know the behavior of mobility as a function of doping, temperature, etc., we can also know the behavior of diffusion coefficient. So mobility as a function of doping and temperature, that is the behavior that one looks for, okay, for characterizing the semiconductor. For this particular parameter, that is mobility, which is equal to q into mean free time between collisions by 2m, we have seen the various scattering phenomena, and we showed that the mean free time between collisions for ionized impurity scattering decreases with increase in total doping or decrease in temperature. Similarly, the lattice scattering, the mean free time between collisions decreases when temperature increases. Then we came to carrier-carrier scattering, and we said that carrier-carrier scattering does not affect the mobility of carriers if the carriers involved are of the same polarity. So scattering of electrons by electrons and scattering of holes by holes will not affect the mobility of electrons or holes. However, the scattering of electrons by holes and vice versa, this can affect the mobility, okay. So in a semiconductor, if electrons are in a majority, then the whole mobility will be affected by scattering with electrons. However, the mobility of electrons will not be affected by scattering because of scattering with holes, because holes are in a small number. So the carrier-carrier scattering affects only the minority carrier mobility in a semiconductor. If the carriers are almost in equal number and their concentration is very high, which can happen if the semiconductor has been injected with a large number of extra electron hole pairs, in such a case also the carrier-carrier scattering can affect the mobility. In such case it will affect the mobility of both electrons and holes, okay, but otherwise it affects only the mobility of minority carriers, and even that happens only at very high doping levels. Now taking ionized impurity scattering and lattice scattering as a dominant scattering mechanisms, we will ignore the carrier-carrier scattering for present, that is in this course. We can write, taking these two into account, the overall mobility formula. Now how do we do that? We can write the equation 1 by tau c, which represents the number of scattering events per unit time, because tau c is the mean free time between collisions. So 1 by tau c, that is the total number of scattering events, is the sum of scattering events due to ionized impurity plus sum of scattering events due to plus all the scattering events due to lattice scattering, okay. So sum of the scattering events due to ionized impurity and lattice scattering. So you add up these two, you get the total number of scattering events. So this is the formula. Now this formula you can easily translate to mobility, because you see from here that tau c is proportional to mobility. So we can therefore write 1 by mobility is equal to 1 by mu ionized impurity plus 1 by mu lattice scattering, okay, due to lattice scattering. So this is the formula. So if you know how mu I and mu L individually depend on doping and temperature, then you know how the mobility depends on doping and temperature, okay. Now it turns out that the mu I and mu L individually depend on temperature as shown in this slide. So mu I varies as T power 3 by 2, this mobility increases with temperature because scattering reduces as a function of temperature. But the scattering increases with doping, so the coefficient alpha is a strong function of total doping and alpha decreases with total doping. For lattice scattering, the formula is delta, a constant delta into T power minus 3 by 2 here. These powers 3 by 2 and minus 3 by 2 are derived from theory. In practice, the powers are somewhat different. Now, in the extrinsic range beyond 300K, the mobility is mostly governed by lattice scattering. So you can take these two segments of the mobility, and this formula shows that whichever mobility is lower, okay, that will decide the overall mobility, right. So whenever mu I is much lower than mu L, the mobility is approximately mu I, and whenever mu L is much less than mu I, the mobility is approximately mu L. So whatever we have written, the behavior as a function of temperature and doping, you can show on a graph as follows. So this is the line. Now here you have mu on a log scale and temperature also on a log scale. We are plotting both on a log scale because mobility versus temperature is a power law behavior, as we saw, okay, T power something. So when you plot log log, you will get a straight line. So this is the straight line corresponding to the lattice scattering. So this is mu L, which is proportional to T power minus 3 by 2, and this is the line corresponding to mu I. So this is mu I, which is proportional to T power 3 by 2. So now if you want to sketch the overall mobility for any given doping as a function of temperature, it would be mu I for low temperatures and mu L for high temperatures, okay. So it will tend to go like that. So this is the behavior of mobility. If you want the mobility for a different doping, for a higher doping, then as we said, the ionized impurity scattering increases with higher doping. So you will get another line here corresponding to a higher doping for ionized impurity scattering, and so your mobility for higher doping will tend to go something like this, okay. So this is increasing doping. And your temperature of 300K would be somewhere here, that is to say that this is room temperature. Beyond room temperature, it is almost lattice scattering that is dominating, okay. Now this is the behavior, exactly it is shown here, okay. This is a practical behavior as a function of doping and temperature. Now if you are interested in knowing the mobility at 300K, okay, then at 300K the mobility as a function of doping is given by this particular graph, okay. Its variation with doping, mobility decrease in doping, with doping, and which can be captured in equations as shown here. So the mobility is equal to mu max minus mu min divided by 1 plus total doping divided by a constant. This ratio is raised to the power gamma plus the minimum mobility. For electrons and holes in silicon at 300K, the values are given in this table. So maximum mobility is 1330 for electrons and 65 and 495 for holes. Minimum mobility is 65.5, that is for very heavy doping levels for electrons, and 47.7 for holes. The unit for mobility is centimeter square per volt second. Similarly, the values of N0 and gamma are also given here. You can use this formula to find out the mobility for any given doping conditions at 300K. And then if you are interested in the mobility at any other temperature, you could use the formula that we showed earlier, that is mobility variation with temperature, okay, and find out what is the mobility. We will consider a solved example to illustrate some of these ideas. Now The mobility is the other important parameter that we have come across in this particular discussion. Earlier we had seen the parameters, namely energy gap of a semiconductor. That was an important parameter. Okay. So mobility, after energy gap, now mobility is the next important material parameter that affects the applications of the semiconductor. So let us look at a picture of mobilities in silicon and gallium arsenide, okay, and see how this mobility behavior affects the these values of the mobility affect the applications of these two semiconductors. So if you compare, for example, the mobility of electrons in gallium arsenide is much higher than mobility of electrons in silicon. You can see at both doping levels, 10 power 14 and 10 power 19. Okay. So this has important consequences on the application. So for example, if you want to make devices which can carry high current or which can work very fast, then gallium arsenide is better than silicon, provided the devices are dependent on only the movement of electrons. Okay. So if you have bipolar transistors such as NPN transistors, or you have MOSFETs or field effect transistors, you cannot say MOSFETs because it is difficult to make MOSFETs in gallium arsenide. Field effect transistors which depend on electrons, that is n-type field effect transistors, then these transistors in gallium arsenide can carry more current and will be faster than in silicon. Okay. So that is the reason why people look for different semiconductors, okay, for making devices. So alternatives to silicon are being considered. So gallium arsenide is one such alternative for high speed devices or high power devices. However, you can see here that the whole mobility in gallium arsenide is comparable to that of silicon. Okay. In fact, it is lower at 10 power 14 per centimeter cube doping level. So this low hole mobility coupled with very high electron mobility creates some problems in the case of gallium arsenide if you are making circuits which require both n-type and p-type devices. So for example, CMOS. If you want to make CMOS type of devices, complementary devices in gallium arsenide in a circuit, then there will be problem because the size of the p-type device will be much larger than that of the n-type device, in order that the p-type device carries the same current as n-type device. In complementary structures, in circuits depending on which are based on complementary devices, there has to be matching between the performance of the p-type and n-type devices. So to achieve this matching, the geometry of the device, in the case of gallium arsenide semiconductors, the p-type device geometry will have to be much higher than n-type geometry. So this creates a lot of problem in laying out. When you have a large number of n-type and p-type devices and you want to interconnect all of these, it creates problems. So complementary type of circuits are not possible in gallium arsenide because of this problem. Okay. So this is how the mobility behavior can affect the applications. The parameter value of the mobility can affect the applications of the semiconductor. Okay. Let me also just mention that the effective mass of silicon and gallium arsenide of electrons and holes, you have to consider both types of effective mass, conductive effective mass and density of states effective mass. So what we have discussed so far in the context of carrier transport, in this context the conductivity effective mass is what is important, okay, whereas the density of states effective mass is important while estimating the carrier concentration, effective density of states and so on. So the differences in these two situations, that is conductivity situation and density of state situation, should be clear by now. Now we will take up the topic of resistivity, because resistivity depends on both carrier concentration and mobility. So if you combine mobility and carrier concentration dependence, what kind of dependence do we get for resistivity as a function of doping and temperature? So let us start with extrinsic silicon first. This is the picture Instead of resistivity, we are plotting the conductivity, which is nothing but the reciprocal of resistivity. So conductivity as a function of temperature. So you find that the conductivity increases from 0, and the region 2 is the extrinsic range. Here in this range the resistivity conductivity increases and then starts falling, and finally when it enters the intrinsic range it increases again. So let us explain this behavior by combining the behavior of mobility and carrier concentration. So extrinsic silicon supposing you take n type, the carrier concentration if you were to sketch as a function of temperature, so electron concentration Nn0, then this behavior on a linear scale is like this. This is the so called extrinsic range, this is the region 2. This is the partial ionization range and this is the intrinsic range. Now if you sketch the mobility on the same graph, okay, so this is carrier concentration, and if you sketch the mobility will be something like this, it will increase and then fall, somewhere it is maximum, okay. For the same doping level we are plotting the mobility, so this is mobility, this is mu n. Now your conductivity sigma is equal to q n mu n plus q p mu p. If you are taking n type semiconductor, then this n is Nn0 and we are considering equilibrium conditions or close to equilibrium conditions, and this is Pn0. Now Pn0 will be much less than Nn0 because these are minority carriers. So your sigma in n type semiconductor is approximately equal to q Nn0 into mu n. So we need not bother about this whole concentration and the whole mobility. So that is why using mu n behavior and Nn0 behavior, all that we need to do is multiply these two curves, okay. So it is evident that you will get a rise and then in this range a fall in resistivity, a fall in conductivity because of fall in mobility. This is happening because of lattice scattering, and then because carrier concentration is increasing you again have rise in mobility, okay. So this is something like this. So that is how one can explain this particular behavior. So this fall here is because of mobility behavior, okay, lattice scattering, and this rise over a small region in the extrinsic range is because of ionized impurity scattering, okay, because in this range the carrier concentration is constant. So whatever variation you see is mainly because of mobility. Now let us look at intrinsic silicon sigma I. So in this case your sigma is q into mu n plus mu p into Ni, because electrons and holes are in equal concentration. So now the behavior of sigma I will depend on mu n, mu p and Ni behavior. Now Ni is increasing continuously, okay, as a function of temperature right from 0 onwards to very high temperatures, and this change in Ni with temperature is very rapid as compared to variation in mobility, okay. So if you combine these two, mu n and mu p have a power law dependence on temperature, whereas Ni has an exponential dependence in addition to the power law. So we can write this as q mu n plus mu p into t power 3 by 2 into exponential of minus Eg by 2 times kT. That is the behavior into some constant A. So if you now also include the power law behavior of mobility, then this will be of the form Q also you absorbed in a constant. Okay, so this will turn out to be of the form some B into T power some A into exponential of minus Eg upon Kt. So you see the resistivity of intrinsic silicon is not going to be very much dependent on the mobility behavior. It is the carrier concentration behavior, because this is the most dominant variation with temperature as compared to the power law variation T power A, where A combines this 3/2 power as well as the power law because of the mobility. It turns out that A is something like -1. If you combine all the power laws and together, A is about -1. Okay. So if you sketch sigma I versus T, the behavior will be the same as that of the carrier concentration behavior. So which means sigma I versus T is same as Ni versus T behavior. So in other words, if you sketch sigma I on a log scale versus 1 by T on the x axis on the linear scale, then you will get a behavior like this, which is same as that of the intrinsic silicon. That is, this will be a straight line, because the mobility behavior only affects the T power A here, this term. And that is why for intrinsic silicon, if you sketch the resistivity, measured resistivity as a reciprocal of temperature, from the slope of that one can easily get the energy gap, because this behavior is similar to that of the Ni behavior, intrinsic carrier concentration behavior, multiplied by some constant. Okay. So the slope of this particular line is nothing but, as you can see from here, the slope of this here it should be 2 times Kt. So if I sketch log sigma I, okay, it will go as is proportional to minus Eg by 2K into 1 by T. That is what you get if you take the log. So slope of this is equal to minus Eg by 2K. From the slope of the resistivity versus reciprocal of temperature graph for intrinsic semiconductor, one can get the energy gap. Now it is time to consider a solved example, okay, to illustrate some of the ideas and to also show how formulae can be used to make calculations. The example is, calculate the following for phosphorus doped silicon whose resistivity is measured as 1 ohm centimeter at 300 K. So what we are supposed to calculate are the following: the impurity concentration, the hole diffusion coefficient at 300 K, the resistivity of the sample at 500 K, and the resistivity of the sample at 300 K on adding 1 into 10 power 16 per centimeter cube atoms of boron. Okay. So basically you have an n-type semiconductor whose resistivity is 1 ohm centimeter at 300 K. So let us start with the first part. What is the impurity concentration? So data given is 1 ohm centimeter at 300 K and it is an n-type phosphorus doped. So what is the impurity concentration? Now as we have seen, the conductivity of this semiconductor we can write as Q n0 into mu n, where ignore the whole component of the conductivity, because only majority carrier concentration decides the conductivity. So the resistivity is 1 by rho, that can be written as 1 by Q nn0 into mu n. Now we know rho and we need to get nn0. So nn0 is equal to 1 by Q into rho into mu n. Now difficulty in applying this particular equation in a straightforward manner is that this mu n depends on the nn0, which we want to determine. Okay. So mu n depends on the doping. Since we don't know the doping in advance, a straightforward use of this relation is not possible. Some involved calculation is required. So one approach to get the impurity concentration, nothing but Nn0. We know that Nd will be Nn0, okay, because we assume at 300 K complete ionization and the majority carrier concentration is almost equal to the doping level, ignoring the thermal generation. So the way one way to solve this problem is to look at a graph of doping versus resistivity, okay. So these kind of graphs are available where resistivity is given as a function of doping concentration N. This is the net doping, okay, for both p type and n type semiconductors. So here you can see the resistivity of 1 ohm centimeter for n type and read out what is the concentration, okay. In this particular graph the finer divisions are not shown, so it is difficult to find out, okay, but in graphs available in books you will find the smaller divisions present and one can determine the concentration from there. Even then, from the graph an accurate determination is very often difficult, so even tables are available for resistivity as a function of doping, which can be used to get the resistivity for a given doping or doping for a given resistivity. Now alternately, if you want to do a calculation using a computer, okay, then it can be done as follows. So what we do is we assume the mobility corresponding to the low doping or the maximum value of mobility here and find out the concentration. Then we use this concentration and do an iteration and find out the mobility corresponding to this concentration using the mobility versus doping formula, okay, and then you use that new value of mobility and determine the concentration again. So when you repeat this calculation 2 times, normally you get a very good result. So if you do that, then the calculation proceeds as follows. So mu n, you use mu n equal to mu n max, that is equal to 1330 centimeter square per volt second, and if you do that, then your Nd is 1 upon q rho into mu n max, which is equal to 1.6 into 10 power minus 19 coulombs. You must always put the units also simultaneously on the side. Rho is 1 ohm centimeter, and this is 1330 centimeter square per volt second. So this is your value of doping and these are your units. So here you can see this gives rise to centimeter cube term and coulomb per second is amperes, okay. So ampere into ohm is volt, so this cancels and you have per centimeter cube as a unit, and the result would be, this will be equal to 4.7 into 10 power 15 per centimeter cube. Now you use this value of doping and find out the mobility. Now your mobility you can write using this formula, 1330 minus 65.5 divided by 1 plus the doping, that is 4.7 into 10 power 15 upon 8.5 into 10 power 16 whole power 0.76. This formula we had shown on the slide earlier, plus 65.5 centimeter per volt second, okay. So you use this formula for mobility as a function of doping at 300 K, and then the result will be a mobility of 1204 centimeter square per volt second instead of 1330 that we assumed earlier. So you use this value of mobility now here instead of mu n max, and you will get the new doping. So the new doping will be 4.7 into 10 power 15 into 1330 divided by the new value of mobility. Basically there is this ratio, and this is nothing but 5.2 into 10 power 15 per centimeter cube. So that is your value of doping or impurity concentration. Now next you need to find out the diffusion coefficient of holes. To find out the diffusion coefficient of holes, that is dP, you can use Einstein relation, mu p into thermal voltage Vt. So you need to know mu p. Now mu p you can find out using a formula similar to this, because you know the doping, okay, like you have a formula for mu n, you have a formula for mu p. So mu p is equal to 495 minus 47.7 divided by 1 plus the doping is 5.2 into 10 power 15 divided by 6.3 into 10 power 16 whole power 0.72 plus 47.7 centimeter square per volt second. Please note that whenever you write the magnitude, you must also write the units, dimensions. You should not forget, otherwise you go wrong in calculations. So this mobility turns out to be equal to 431 centimeter square per volt second, and therefore your dP is 431 into 0.026. You see centimeter square per volt second, and this is volts, so volts will cancel and you will get centimeter square per second as the unit, and this will be 11.2. So that is your diffusion coefficient. Okay. Now the part C is the resistivity of the sample at 500 K. So to find out the resistivity at 500 K, we need to check two things. So resistivity at 500 K. What we need to check is the minority carrier concentration important, because this temperature is high. So will the whole concentration be important, and will it make a difference to the resistivity? So for this purpose we need to find out the intrinsic concentration first. So Ni at 500 K. Now this we can find out very easily, as we had done earlier in this course. You can write this in terms of Ni at 300 K into 500 upon 300 whole power 3 by 2 into exponential of minus 1.12, which is the energy gap, divided by 2 times Kt, where T is the room temperature, that is 0.052, into the room temperature, which is 300, by the temperature of interest, that is 500 minus 1. Okay. So you make this calculation and you will get the result as 1.78 into 10 power 14 per centimeter cube. Okay. Now the minority carrier concentration would be, that is Pn0 is equal to Ni square by Nn0, which is Ni square upon the doping, so which will be equal to 1.78 into 10 power 14 square upon doping is 5.2 into 10 power 15, and evidently since this is 10 power 28 and this is 10 power 15, Okay. So your order of this particular result will be 10 power 13. So this is of the order of 10 power 13, which is much less than 5.2 into 10 power 15 per centimeter cube. Okay. So what we find is Pn0 is much less than Nn0. So result is Pn0 is much less than Nn0. So we can still continue to use the relation sigma is equal to is approximately equal to q mu n Nn0. We are neglecting any contribution of Pn0 to the mobility to the resistivity. So this Nn0 is nothing but the doping. So this we can replace by Nd, which we already know. However, the mobility at 500 K will not be the same as mobility at 300 K. So we need to determine mobility at 500 K, and then we can easily determine the conductivity or resistivity. So mobility at 500 K. So mobility at 500 K by mobility at 300 K can be written as is equal to 500 by 300 whole power minus 3 by 2. This is because we are using the fact that in the extrinsic range above room temperature, the mobility approximately goes as T power minus 3 by 2. Okay. So mu is equal to some constant into T power minus 3 by 2. So this is the relation we are using. So from here we find that mobility at 500 K is equal to mobility at 300 K for electrons. So this is mu n. And the result at 300 K, your mobility was 1204 centimeter square per volt second. So this is equal to into 3 by 5 whole power 3 by 2, which is equal to 559.6 centimeter square per volt second. So that is the mobility. Now you can use this mobility here and then find out the resistivity. So 1 by rho is approximately equal to 1 by q mu n in d, and in fact we could directly substitute this value of mobility, or alternately what we find is, since the resistivity is dependent on the mobility behavior, we can write whatever we have written in terms of mobility directly as an equation in terms of resistivity. So we can, for example, write rho at 500 K divided by rho at 300 K. Okay. So rho is, sorry, here it is rho, it is not 1 by rho. So rho is inversely proportional to mobility. So this is equal to the mobility at 300 K divided by mobility at 500 K of electrons in this case. And this is equal to 5 by 3 whole power 3 by 2. And the result therefore is resistivity at 500 K is equal to 300 K resistivity, which is 1 ohm centimeter, multiplied by this term, and the result would be 2.15 ohm centimeter. So this is the way one can find out the resistivity at a different temperature, okay, higher temperature. So you can find out the mobility at a higher temperature and find out the resistivity, but since we already know the resistivity at lower temperature, okay, it is easier to write it in this form, simplified form, and then get the resistivity. So you see at higher temperature actually the resistivity has increased, okay, because of the fall in mobility. Now we have the final result, the final part of the example that we have to show, and this is the resistivity of the sample at 300 K on adding 1 into 10 power 16 per centimeter cube atoms of boron. Now this means that we have a compensated semiconductor with donor type impurity of doping 5.2 into 10 power 15 per centimeter cube and an acceptor doping of 1 into 10 power 16 per centimeter cube, and you want to know the resistivity if you have this. Now clearly this is a p type semiconductor now, because Na is more than Nd. So the carrier concentration of holes, that is the majority carrier concentration, would be, in this case, Pp0 can be written as Na minus Nd. All impurities are ionized, and now we can neglect the electron concentration, okay, because thermal generation minority carrier concentration will be very small, and this is equal to 4.8 into 10 power 15 per centimeter cube. Now this is a p type semiconductor with this particular concentration of holes, okay. Now the resistivity can be written as 1 by Q into Pp0 into mu p, where Pp0 is given here. Now mu p we have to determine. We cannot use the whole mobility that we had determined earlier in this case. Why? Because now we have to use total doping of this plus this. The mobility of holes which we had determined earlier in context of the diffusion coefficient calculation was only because of this particular doping. So we need to recalculate the whole mobility. So we use the formula mu p is equal to 495 minus 47.7 divided by 1 plus, now here 6.3 into 10 power 16 is in the denominator and power is 0.72. In the numerator we will have to put the sum of this Nd plus Na, okay. So which is equal to 1.52 into 10 power 16 and plus 47.7 centimeter square per volt second. This is the whole mobility, and the result is 377 centimeter square per volt second. That is the whole mobility. So now we can substitute this Pp0, that is this 4.8 into 10 power 15 here, and 377 centimeter square per volt second here, and your resistivity would be Q into Pp0 into mu n, mu p, 377. This is the resistivity, and of course your unit will be ohm centimeter, because this is in coulombs, this is per centimeter cube, and this centimeter square per volt second. We have shown that if you use these units you will get resistivity in ohm centimeter, and the result is 3.46 ohm centimeter. So the resistivity has actually increased because the sample has become p type and hole mobility is smaller than electron mobility. Because of combination of these factors you are getting this resistivity, okay. So this is how one can make calculations of resistivity at different temperatures and different doping conditions, okay, and this example should clarify many of the ideas that we have so far discussed. The next topic that we will discuss before closing this particular carrier transport discussion will be how do you see the mechanism of drift from the energy band point of view? Even diffusion can be seen also from energy band point of view, but we will see how the drift is seen from the energy band point of view, and one can work out for diffusion also, okay, in the same manner. So we need to draw the energy band diagram of a semiconductor in which a drift current is flowing. Suppose this is a semiconductor, let us assume an N type for simplicity. We can use P type also, it does not matter really. So in the semiconductor, the electric field is in this direction. So this is the direction of electric field. Now what would be the energy band diagram under this condition? We will assume a uniform semiconductor. So which means that the electric field is also going to be uniform, and that means that the potential will vary linearly as you move from the left end to the right end. So this is positive and this is negative. Now how do we draw the energy band diagram under these conditions? Now recall that the vertical axis in energy band diagram shows electronic energy. So increasing electronic energy. Now we have also mentioned earlier in the discussion on energy band diagram that EC represents the potential energy of the free electron, okay, and EV represents the potential energy of a hole. So the energy band diagram without an electric field, if you want to draw, it would look something like this. This is EC, this is EV. This is the potential energy of the free electron, this is the potential energy of the hole, okay, and this is the first time that the diagram is drawn with distance as the x-axis, okay. So this is energy and this is distance along the sample. So this is a sample. No electric field is applied. So these are under equilibrium conditions. So your Fermi level here would be somewhere here, this is Fermi level. This dotted line shows the intrinsic level. So EC is the potential energy of a free electron, okay, and this is electronic energy. So which means that whichever side is negative, whichever position here in the sample is negative, there the potential energy, the electronic potential energy should be shown higher, and whichever side is positive. So let us look at this sample now. This side is positive, so here on this side your EC will be lower. So when you draw the energy band diagram, it will be drawn something like this. So this is energy and electronic energy. So it would be drawn something like this. This is your EC, potential energy of the electron, free electron. This is lower and this is higher because this is negative, more negative. As you move up, you have higher and higher electronic energy. The valence band edge EV will run parallel to the conduction band edge. This is because when you apply a voltage, the energy gap does not change in the semiconductor. The carrier concentration is also not changing. So the structure of the silicon is not changing. Only thing that is happening is that you are superimposing an electric field. So energy gap cannot change with distance. So that is why this edge EC is parallel to EV, and this difference remains equal to energy gap. Now what is the slope of this particular diagram? Okay. Slope of this diagram is nothing but slope of the potential. EC is energy. If you divide EC by Q, you get the potential. Now your equation is electric field E is equal to minus d psi by dx, where psi is the potential of a positive charge. Okay. So when you write electric field equal to gradient of potential, this is potential of a positive charge. So if you want to write in terms of a negative potential, okay, then this negative sign will go away. Now it is important to note here that the E here is the electric field, whereas the E here is the energy. Okay. So I hope there will not be any confusion, because we have been using this nomenclature throughout the earlier lectures. So therefore in terms of EC, if I want to write down the replace psi by potential EC, then I can write the same thing as this is equal to d of EC by Q, because I want to convert energy into potential, so I have to divide by charge, by dx. The negative sign has been removed because this EC by Q is electronic potential. So in other words, what we find is that the electric field is equal to 1 by Q and dEC by dx. So now you can clearly see that the slope of this line is positive, 1 by Q dEC by dx, and therefore the electric field is in the positive direction, as you can see, left to right. And the slope of this particular line gives you the electric field, provided you take into account the charge Q. So that is the important thing that you see for the energy band diagram when you apply an electric field. Okay. Now on this particular diagram, how will you show the motion of an electron? Electron will move from right to left because it will move against the electric field. Now this motion can be shown as follows. Let us say electron starts from here. Now after collision, it has started moving in this direction towards the left. So it moves like this, and it encounters a collision at somewhere here. At the end of the collision, the energy gained in the direction of the electric field is randomized. So in other words, we can show this as the energy has dropped to, the kinetic energy has got dropped to 0, because this difference represents the kinetic energy of the electron that it has gained from the electric field, and then it starts again moving and encounters a collision and so on. So this is the path. Now note here carefully that this is a horizontal line. Okay, so this line is not going up nor is it moving down, it is perfectly horizontal. Now this is because the total energy of the electron between two collisions remains constant. It is losing potential energy as is shown by this line, but it is gaining kinetic energy. Okay, so loss in potential energy is exactly equal to the gain in kinetic energy. So total energy being constant is shown as a horizontal line. So this is electronic energy. Total electronic energy between collisions is constant, but it is gaining kinetic energy. That is seen by the fact that this line here, for example, is above this particular line and there is a gap. This gap represents the kinetic energy that is gained from the electric field. Now one can similarly draw the movement of the hole on the energy band diagram. So it would be something like this. The hole moves in this direction. So this is electron and this is hole. This is X in the sample. So this is how one can look at the drift from energy band point of view. Note carefully that I have not shown the Fermi level here, because Fermi level is strictly an equilibrium concept, and under non-equilibrium conditions one can extend this idea, but then one has to introduce what are called quasi-Fermi levels. Okay? So this aspect we will consider later. So I am not showing the Fermi level in this diagram. It is not necessary to show this level to understand the drift transport. Now let us summarize our discussion on carrier transport. So we covered the following topics in order. First, the example of various modes of transport, such as drift, diffusion, thermoelectric current, and current because of tunneling. Random thermal motion of carriers. The semi-classical phenomena, drift, diffusion, and thermoelectric current, are based on this particular motion. Then scattering mechanisms which cause the random thermal motion. Then we considered the drift and diffusion transport, how directed motion is superimposed over random motion by application of potential gradient or concentration gradient. Then we discussed relation between mobility and diffusivity. This is the Einstein relation. Then we discussed the mobility as a function of doping temperature and electric field. So for small fields you have a linear relation between velocity and electric field, but for large fields the velocity is constant. So mobility varies with field. Then we discussed resistivity as a function of temperature and doping, and finally we discussed the drift from energy band point of view. Next we will consider the topic of excess carriers in the next class.